Hi team, I'm going to do just a couple more examples of L'Hopital's rule. And that again looks like this. And you should check that out. I think it's in chapter 7, but I'm sure you can figure out how to use a table of contents to practice these. A little bit of history here. L'Hopital bought this rule from the Bernoulli brothers. The Bernoulli brothers were really great mathematicians. They were Italian, and L'Hopital was obviously French. And back in the day, it was a pretty big deal to discover something in math. And so the Bernoulli brothers were really, really good at that, but the Italian economy wasn't such that they were getting really paid for it. So they figured out L'Hopital's rule, which is that little bit about, the speed of the top versus the speed of the bottom, depicting how the indeterminate form works out. And then they sold it to L'Hopital for a giant pile of money. Then L'Hopital publishes the first calculus textbook, puts his name next to it, and now he gets it forever. So anyways, there's that. So here's an example, right? So here's example 2. Let's try this guy. And all I'm doing here when I'm making these problems up is just trying to think of things that will come up with indeterminate forms, like this guy. If I plug in 4, I get 16 minus 16, which is 0. Right? So the top goes to 0. And then, of course, 4 minus 4 is 0. Now, this probably makes something, right? This probably actually equals 1 or 2 or 3 or 4 or something. But, it's probably not either 0 or, something over 0, which is infinity. So probably not 0 or infinity. So what is it? Well, we can use L'Hopital's rule because it's indeterminate, and so we can take the derivative of them both. So if we L'Hopital this, we get the same limit as x goes to 4, but we get 2x minus 0 all over 1, because that's the derivative of the bottom. Now you can go ahead and plug your old limit in and have some fun with it, and 2 goes into there, and you end up with 8. So this one actually approaches 8, which, is reasonable because it's between 0 and infinity. So this one actually has a limit and it goes to 8. You could have done this one a totally different way. So you could have realized that this is the difference of squares. And I'm only pointing this out because those of you who are going to take an entrance exam into a college with math, they're going to put a difference of squares on there. And it will probably be this exact one, to tell you the truth. Or this might be a 9 and this might be a 3. Or a 4 and a 2. Whatever. And they're going to want you to see this as the limit as x goes to 4 of x plus 4, x minus 4, all over x minus 4. And then you can cancel those 2 out and get 4 plus 4 equals 8, which is the same answer twice. So this is how they'd want you to do it on an entrance exam. But I care if you use L'Hopital's rule, right? I mean, just realize it's indeterminate and that the rate of the top and the rate of the bottom. So is what actually matters, which is why we can use the derivative. Again, this is the rate of the top, and this is the rate of the bottom. This one is going up by 1, while this one goes up by 2x. So the top wins, right? But the bottom kind of cuts it down to size. So we don't actually get all the way to 0 or infinity. Okay, let's try a different example. So here is example 53.9. And you can fast forward through this next bit. I'm going to draw a shark. So, right, so here's this, and then a shark like that. And it's got huge teeth, like this, and angry eyebrows because it's a shark. I don't know if sharks are actually that mad, or if it's just their personalities, or it's just kind of how evolution had them, get bit or get figured out. And I don't know, evolution's a weird thing. It's not like it wanted sharks to be mean, but that's what it got. So there's a shark, right? That has nothing to do with that. You should fast forward until it do that. So let's try this one again. Example 3. What if we had the limit as x goes to infinity of e to the x over x squared? What happens then? Well, this is for sure indeterminate, right? Because e to the infinity over infinity squared is infinity over infinity. And what is that? If the top wins here, then the thing goes to infinity. If the bottom gets to infinity first, then the whole thing goes to 0. So again, we have that situation. What is it, 0 or infinity? Well, I don't know. Let's figure it out. We can use L'Hopital's rule and get the limit as x goes to infinity of e to the x all over 2x. Okay, so plug that back in. You get e to the infinity over 2 times infinity, which is not helpful. You get infinity over infinity again. But you'll notice here that this is definitely way slower than that, right? So the denominator is going to quit here on us if we do it one more time. And again, this is still indeterminate, right? This is just as indeterminate as that. So it's almost like this didn't even happen right here, and we can just do it again. So L'Hopital it again, and you can get the limit as x goes to infinity of e to the x again, because the derivative of the top. Remember, we're not doing the quotient rule. Not quotient rule. No more than 4 letters either. That's going to drive me nuts. So this is not the quotient rule. So this one here becomes a 2, right? We're literally talking about the speeds of the top and the bottom. We're not interested in the slope of this as a function. We're not talking about that. We're using a derivative as a measurement of speed of individual pieces. And then this guy, if you plug in infinity, you get e to the infinity over 2, which last time I checked was infinity. And obviously it's going to be infinity because e to the x is way faster than x squared. So this one gets to infinity way before this one does. So you end up with infinity divided by a number. Boom. Infinity. And that kind of looks like a face, doesn't it? Eyebrows. Okay, moving on. Last example, and then you guys can get to work at chapter 7. I believe this is example 5.-3. I don't think the Romans had negative numbers, now that I think about it. I wonder how they did that. I don't know. So what if we have the limit as x goes to 0 of x times ln x? Okay? I don't know what to do here because this is an indeterminate form, but it's not one of the ones we like. So if you remember back to the very beginning, let me rewind my PowerPoint here. If you remember, go back to the very beginning. The rule was, as long as this fraction produces one of these indeterminate forms. However, there are a lot of indeterminate forms. These are the only 2 that apply to L'Hopital. These other ones, or like the one we're about to see, which is 0 times infinity, these ones don't work because they don't use the sort of rate fraction trick. And so this one gives us something like 0 times ln of 0, which last time I checked is 0 times negative infinity. And that's bad news bears. So which one is it? If ln x gets to this first, then it's negative infinity. If x gets to 0 first, then the whole thing gets multiplied by 0, and the whole thing's nothing. So again, we're in the infinity or 0 problem. So what we have to do is create a L'Hopital form. So what we're going to do is do a little piece of algebra here that's going to make this look stupid, but work out better. So I'm going to turn this into the reciprocal of a reciprocal. Why? Because it gets me the fraction, which is what L'Hopital is good at. So I get ln x over 1 over x, which gives me ln of 0 or 1 over 0. So now this numerator goes to negative infinity, and this denominator goes to infinity, which is one of the L'Hopital indeterminate forms. So now we can go ahead and L'Hopital this, which is not a verb. You shouldn't say that. It might be something very vulgar in French. I don't know. And so you end up having to do the derivative of the top and the bottom. So you end up with 1 over x on the top, and you end up with negative 1 over x squared on the bottom. Please don't ask me how I got the negative sign. It'll make me go insane. I'm not even there, but I'll hear you ask it from Iowa City and then go insane wherever I'm at. So please don't. This is a negative 1 right here secretly. Okay. So now we can go ahead and see what happens here. So if I plug in 0, I end up with 1 over 0 again, 1 over 0 again. But there's some simplification I can do here to make this a lot easier. So this equals the limit as x goes to 0. And this is the reciprocal of a reciprocal. So we're going to end up bumping this up here and this down here. So we end up with a negative sign, we end up with x squared on the top, and we end up with x on the bottom. These cancel out, and so we end up with the limit as x goes to 0 of negative x. So this goes to 0. Okay? And you can graph all of these if you want to check them out. This one's really important. There's gonna be a lot of them in the book that you're trying that you won't be very good at, and it's because it'll look like this, and you'll need to make this adjustment right here. So x is the same as 1 over x, the reciprocal of a reciprocal. This is the little magic trick that you're going to find difficult. So if you can't do one, this is probably what you're not seeing. Okay, guys, miss you a lot. I'll see you guys on Wednesday. Feel free to email me and take pictures of your math if you have a problem. Have a good day.